When your business relies on cryptography, the most valuable asset isn't the algorithm, it's the keys. A hardware security module, or HSM, is a specialized device that protects those keys and performs critical cryptographic operations inside hardened, tamper-resistant hardware. If cryptographic keys live in a normal software stack, they're constantly exposed to multiple layers of risk. Keys in RAM can be captured through memory scraping tools or malware. Keys on disk can leak through backups, snapshots, or insider access. And if the operating system is compromised, an attacker can often read both memory and storage, bypassing your application's controls. Once an attacker gets a key, they don't need to break your crypto anymore. They simply impersonate you. That's why protecting keys inside general-purpose servers is fundamentally fragile. An HSM creates a hardened trust boundary. Inside that boundary, cryptographic keys are generated, stored, and used without ever leaving the device in plain text. The hardware is purpose-built with protections against probing, side-channel attacks, and firmware tampering. If someone tries to open or modify it, the device can detect that and erase sensitive material. Equally important is isolated execution. Cryptographic operations run in a controlled environment, separated from the general operating system and application stack, which dramatically shrinks the attack surface. Strong cryptography starts with strong randomness. An HSM uses a hardware random number generator that samples messy, unpredictable physical processes, instead of relying on deterministic software. That raw noise is cleaned up into high-quality entropy and used to create keys directly inside the secure boundary. Policies can enforce which algorithms and key sizes are allowed, so weak or non-compliant keys simply never exist. And because those keys never leave the HSM in plain text, offline theft becomes dramatically harder for an attacker. Complete lifecycle isolation means the key is protected from birth to death. It's generated inside a specific HSM or security domain and is never supposed to leave that boundary in plain text. Applications can ask the HSM to use the key, but even powerful admins can't simply extract it. Every stage, creation, use, rotation, and destruction, is governed by strong roles and policies. Who can create keys, who can use them, and who can rotate or delete them is all explicitly controlled, logged, and auditable. Here's the mental model to keep in mind. The HSM is a cryptographic black box. Your applications send plain text or hashes in and get ciphertext or digital signatures back out. The crucial point is that the secret keys never leave that protected boundary. All operations happen next to the keys instead of moving the keys to the application. This both reduces the attack surface and offloads heavy cryptographic work from your servers, so you gain stronger key protection and better performance at the same time. When keys need to move between systems, we never ship the raw data encryption key. Instead, we wrap it with another key, called a key encryption key, or KEK, that stays protected by an HSM. The HSM uses the KEK to encrypt the DEK, producing an opaque blob. That blob can be backed up, replicated to a disaster recovery site, or migrated to a new environment. At the destination, another HSM holding the KEK unwraps the DEK. Throughout the entire journey, the actual data key is only ever visible inside trusted hardware. You can think of the HSM cluster as the cryptographic heart of your organization. At the trust layer, it protects your PKI routes and issuing CAs, so the keys to the kingdom never leave hardware. For payments, it secures PIN blocks and card data, enabling compliance with PCI requirements. Across the enterprise, it holds keys for TLS offloading and transparent data encryption, taking heavy crypto work off application servers. And for digital signing, it safeguards qualified signature and seal keys, helping you meet eIDAS and similar regulations with strong, auditable key protection. Comparing software-only crypto with HSM-backed crypto is really about where your keys live and who can realistically touch them. In software, keys sit in RAM or on disk, side by side with malware, buggy code, and potentially rogue admins. Memory scraping, OS compromise, or simple misconfigurations can expose everything. With an HSM, keys never enter host memory and are designed to be non-extractable. You also gain physical tamper resistance and the option of FIP's validated assurance, which is what regulators and high assurance environments increasingly expect. Tamper protection in an HSM works like a cascade. First, something suspicious happens. Voltage glitches, temperature changes, the cover opening. Sensors detect that anomaly and immediately signal the security logic. Next, physical defenses kick in. Things like meshes, epoxy, or active shielding to slow the attacker down. But the crucial step is zeroization. The HSM wipes all sensitive keys from memory, often in microseconds. For FIPS 102 and 103, the standard cares less about being unbreakable and more about guaranteeing keys are destroyed before an attacker can extract them. When you're deciding whether you really need an HSM, think in two dimensions: the impact of a key compromise and how strict your regulators are. If losing the keys would be annoying but not fatal, and regulation is light, pure software, or a basic cloud, KMS is usually fine. As impact rises or compliance tightens, you move toward managed cloud HSMs. Once both are high, payments, eIDAS qualified signatures, core banking or telecom, hardware isn't optional anymore. It becomes a mandatory control, not an optimization. The core idea to remember is this: strong security starts where keys are born and where they live. With HSMs, keys are generated from real hardware entropy. They never appear in host memory, and every critical crypto operation runs inside a tamper-resistant boundary. That's how you turn cryptography from best effort software into a concrete, auditable, compliance-ready control.